In this video, we're going to talk about the two general types of system configurations that we can have. The first is an open loop system. And in an open loop system, we have no feedback going from the output to the input. And so what this means is that with an open loop system, we cannot compensate for disturbances. And so the system that we looked at in the previous video, which I've copied here below, is an example of an open loop system. And so the reason that we can tell this is an open loop system is we see that there's no signal coming from our output over here on the right back to our input. So whatever we're telling the system to do, we just assume that that message is getting relayed all the way through to the output, and essentially our input has no idea that we have these two disturbances sort of coming into play. One example, a simple example of an open loop system would just be a simple toaster or a toaster oven in sort of just a normal house. And so the reason this would be an open loop system is you just put in an input saying how much you want your bread toasted, but the system, the toaster, is not able to account for various types of breads, various bread thicknesses. It's just going to do it for a predefined amount of time. Now, of course, we could adapt that, and we'll talk about that after we've introduced the second type of system, which is a closed loop system. So a closed loop or feedback control system is going to provide a feedback path from the output, which is going to affect our input signal, or as I've called it here, the controller's driving signal. So let's look at what this system looks like. So here's an example of this. So we notice the top part of this looks pretty similar to the open loop system that we saw above. The main difference is now we have this feedback path which is coming from our output and ultimately being combined with this summing junction to our input signal. Of course, it's on the other side of that input transducer, but remember that's just to get sort of the input form in what we need for our controller. So now what we can do is we can account for these two disturbances, disturbance 1 and disturbance 2, and we can make adjustments. So our closed loop system then can accommodate or can account for disturbances. And so ultimately what that is going to mean is that with our closed loop system, we're going to have more accuracy. So we're going to have our output signal is going to be closer to whatever our reference or our input is, because we're able to sort of check along the way to make sure it's actually doing what we want it to do. Just some terminology, this signal right here that is coming out of that summing junction after we've compared our input and our output is called our actuating signal. Now, there's sort of a special case if we have unity gain transducers. So that means if our gain here is 1 and our gain here is 1, so what that would mean is that we actually have our input here and our output here, such that our signal there in that highlighted purple area is just going to be the difference of our input and output. So in that special case, so if we have unity gain on our transducers, then we're going to call this signal our error signal. And we'll talk about this a little bit more in a later unit. And so something I've kind of glossed over a little bit there is, of course, we've not seen this before, but in the previous video, all of our summing junctions just had positive signs. Here we have a negative sign indicating that we're subtracting the signal. And so that's this idea of feedback and how to analyze this is something that we're going to come back and hit on pretty hard in some of the later units. So if we think about our toaster example, so we could implement a toaster using a closed loop system. So say, for example, maybe we come through here and we add some type of camera. So maybe we add a camera and our camera is able to tell us the color of our toast, of the bread surface. Maybe we have other types of sensors that we can use to monitor the level of toastedness of our bread. So with that in mind, why would we want to use these open loop systems if we can have these closed loop systems that can account for disturbances? So we can ask ourselves the question, why use open loop. So think about that for a second, maybe even pause the video. So why use open loop systems? So it seems like if we can get more accuracy with a closed loop system, wouldn't that be preferable in pretty much any application? And so the answer, of course, is yes, more accuracy would always be better in theory, but we have to realize that we're actually constructing these systems. So why would we use open loop systems over closed loop systems? Well, they're cheaper and generally they're going to be less complex. So cheaper and less complex. So what we're going to see throughout sort of this class is there's always going to be these sort of trade-offs in our design process. So in this case, if we go to our toaster example, of course, if we're adding cameras into our toaster, that's going to increase our price. And if we think about it in terms of marketing, if a consumer is going into the store and they see this toaster that's going to provide you a better quality of toast exactly how you want it every time, but maybe it costs $50 more than a normal toaster, you know, most people probably aren't going to buy that. So we need to keep in mind there are applications where we want to have open loop systems, and there are applications where we need to have closed loop systems, and we just need to keep those trade-offs in mind as we're designing.